Today's topics are starting with the creation of a more complex case than we did last week in our first day, which was an IFA antenna, so a PCB design. Today we'll be creating a wire antenna, so a helical antenna in Recad. And to do so, we're going to be using some additional tools that we've included in our skin of Recad. And then we're going to be setting up that same helical antenna in CENOS. And finally, we'll be briefly going over the results. And basically, what is a helical antenna? A helical antenna is a wire antenna that is in a helical shape. As you can see on the right-hand side of the picture, it has two main modes of operation, a normal mode and an axial mode. So a normal mode basically works like a dipole antenna. And an axial mode is basically the directional antenna mode. And it's widely used in radio and satellite communications. And the general workflow is to open up CENOS and to open up Recad, define the parameters, create a wireframe of the helix and the feed line. Then we'll add the volume to the wire using the tools that I mentioned in Recad. Then we'll create all the other necessary objects, such as the ground plane and the dielectric for the coaxial connector. Then we're going to send all that geometry to CENOS and continue the setup there. And then finally, we're going to be running the case. So our end goal is a complex RF model made in Recad and CENOS from scratch. It's going to be a fully parameterized helical antenna model, and we'll have the results for it ready as well. So let's just jump right into it. So let me share my screen. So it should be visible right now. So let's boot up Recad. So I went over the initial splash screen last week. So if you missed that, check our YouTube channel. And let's create a case for it. So let's call this webinar helix. And it's going to boot up Recad for us. So basically, we're going to be using something called a create primitives tool, which allows us to choose from a set of different options, mainly just like basic shapes. So on top, you see here, create cubes and solids and some other primitive shapes. There's also a creation of parameterized geometric primitives. And once we click that, we'll be greeted by the options on the left-hand side, where we can choose from creating a plane, a box, and as you can see here, you can also create a helix. So let's place that down in the model. So as you can see, we have this wireframe of a helix, and let's actually apply some parameters to it. So let's go into the CENOS parameters and define some parameters that we're going to be using today. So first off, I'm going to define the pitch. So that means the spacing between each winding of the helix. So let's call that pitch and define it as 32.5 millimeters. Next up, I'll be defining the turns. So how many turns is going to wind around with. That will be 5 for this demonstration. Next up will be the overall length of the helix. And let's call that helix underscore length. Actually, no, let's call it height. Yes, and that is going to be actually a calculation of the previous two parameters. So we'll take the pitch, and then we're going to multiply it by the turns. And press enter, and as you can see, we have a value here, which is 162.5 millimeters. Next up, let's define the wire diameter. That's going to be 3 millimeters. Next up is the helix diameter itself. So how wide will be the windings overall? So helix diameter, let's make it 41.38 millimeters. Next up, we have the feed line. So our helix is going to start at the at the cross points of all the axes. And we're going to create the feed line going downwards. So let's define the feed line length. That's going to be 5 millimeters. And last but not least, let's define the ground and coax parameters. So let me just copy that in. So it's going to be our radius, ground thickness, and ground radius. So let's go back to the main screen where we have our helix wireframe. And let's go back into the properties of it. And let's start defining our parameters. So as you can see, we have pitch, height, radius, angle, coordinate system, and so on. And let's start with the pitch. So let me select the formula editor button, and then we'll be calling our parameters that we just defined. So let's call the spreadsheet CENOS parameters and call the parameter that we defined for it. So pitch, enter, and we have defined our pitch. So right now it looks like we just have a single line, but we'll update that as we go. So let's define the parameter for the height. Call CENOS parameters, call helix height, press enter, and then we have a much longer line that's slightly squiggling. Next up is the radius for the helix. So let's call the helix diameter. But since we are asked for the radius, we're going to have to divide that diameter by 2. And as you can see, we have a much better looking helix here. And now I want the start point of the helix to be in the absolute middle of the model. So I'll go into the location part of the properties and select the formula editor for the X position. And we'll be calling the parameter for the diameter. So helix diameter, and divide that by 2. But as you can see, it has moved it not to the ideal position that we want. That means I'll have to basically add a minus, so it is moved to the opposite direction. And as you can see, it starts from the center position and goes upwards. So that is it for our helix. And now that I mentioned that we are going to be adding a feed line, so let's do that using the Sketcher workbench. So I'll open up the Sketcher and create a new sketch on the Z and X plane. And as you can see, we have a sort of a sine wave going upwards. And we'll be defining the feed line as a singular line in the model. So let's just place down the line. And now let's apply some fixed lengths to it. So I'm going to be using this feed line also as the inner conductor of the coax. So let's define the length for it. I'll call the formula editor and call the parameters that we need. So first off, we need the feed line length. And then we also need to add the amount of the wire that's going to be inside the coax. So let's call CENOS parameters and add ground thickness. And this will make sense in a moment once you actually start defining the ground plane. And now I want to affix it to the point where the helix starts. So I'm going to be using a coincidence constraint, which will make the top of the feed line touch the starting point of the helix. And now we have a fully constrained sketch, which is shown by the solver. And now I can't really move the feed line anymore. So let me exit that. And as you can see, we have this basically just a wire of no volume. And we're going to be fixing that by using a tool that CENOS has provided in the skin of Recad. And to do that, we have to go back to the part workbench. Select, actually, let's change the name for the helix to helix underscore wire. And select everything that we want to apply a fixed volume to. So we're going to be selecting our 2 objects. And on the top, we'll find the tool called Apply a Thickness to a 1D wire. So what we have done so far is create a 1D helix and a 1D sketch of the feed line. Press that, and let's just use the same parameters that we see here. And as you can see, we have applied the volume to our wires. So that works for us. So next up, we should probably rename this. Okay, not yet, but let's apply the parameter wire diameter that we defined previously in the parameters. So in the properties tab of the wire thickness object, we will be defining the CENOS parameters, wire diameter, and as you can see, it has now become the thickness that we want it to be. Great. So next up, as you probably have already noticed, we have this strange gap in the model, and that is due to how the wire thickness tool creates the wire. Ideally, I want to add something like a solder joint to these parts. And to do this, we're going to be actually creating a sphere to serve as our solder joint. So let's plop down the sphere in the model. And as you can see, it's a bit too large for us. So we'll be changing the size in the parameters for the sphere on the left-hand side. So I want the radius for the sphere to ideally be the same as the wire. So let's call CENOS parameters, wire diameter. And since we need the radius, we're going to be dividing that by 2. And as you can see, we have created sort of a smooth solder joint. So let's combine these objects into a single one using the Boolean operation called fusion, union. And as you can see, it looks much better now. So we basically have our helix ready. So let me rename the fusion to something that we'll know in the future. So helix. And next up, we are going to be defining the ground plane. So let me do this first. So to create the ground plane, we're actually going to be using 2 tools. So first off, for the general ground plane disk, we're going to be using a cylinder. And we're going to need another cylinder afterwards to cut out the hole for the inner dielectric and the dielectric of the coax and the inner conductor. So let's change the parameters to fit our needs. So I want the ground plane disk to be the radius of the ground. So ground radius. As you can see, we now have a disk of the set size. And let's also make it a parameterized ground thickness. So change the height to CENOS parameters dot ground underscore thickness. So nothing changed because it's the same value as the default parameter. Now I want to make a cutout in the disk as well. So let's add another cylinder by clicking on top and define the parameters that we defined before. So radius should be the outer radius of the dielectrics tube. So CENOS parameters dot outer radius. And ideally, we also want it to be the same height as the ground thickness. So CENOS parameters, ground thickness. And now let's use another Boolean operation to cut the hole in it. So I'll select first the ground disk, and then I'll select the shape I want to cut with. And then I'll press make cut. And as you can see, we have a cut in our disk now. So next up, let's add the tube for the dielectric. So we'll use the create tube, and we'll assign the parameters immediately as well. So we want the outer radius to be CENOS parameters, outer radius. And I want the inner radius to be the same as the wire thicknesses. So CENOS parameters, wire diameter, divide that by 2 since we need the radius, and press OK. So also the height should also be the same as the ground. So ground thickness. And now we have our disk and the dielectric. So if I enable the visibility for the helix again, you'll see that it is overlapping. So I want to make this be the bottom of the ground plane to be at the same height as the bottom of the inner conductor. So to do this, we'll be adding parameters to the tube and the ground, which I'll name the same as I just said. And let's choose the placement in the properties of the ground and change the position. And we'll be changing the Z placement. Open up the formula editor, and let's call 2 parameters. So because we changed the length of the feed line to take into account both the feed line length and the ground thickness, we need to place it aptly. So let's call CENOS parameters ground thickness, and let's add the parameter for the feed line length. So it's going to be the same size as the line that we defined before. And once we press enter and press recompute object, it's going to place that above, since I did not add the negative parameter to make it go on the negative section of the Z axis. So let's place the formula that we created in parentheses and add a minus to the beginning of the equation. And once we press recompute, you can see that it is indeed in the same plane as the inner conductor. But now we have to do the same for the tube. And I don't really want to write the whole equation again. I'll just copy that using Control-C, go back to the tube, and change the position of the Z axis to be the same using Control-V. And let's recompute both of these objects. And as you can see, we have our finished model. So this is a bit of a more complex model, but as you can see, it was pretty easy to create this as well. So yeah, since we now have a fully parameterized model of the helical antenna, we can just go ahead and send all of the geometry that we could just created to CENOS. To do this, we just have to select all of the parameters all of the objects that we want to send, and then press send to CENOS. And now we open up CENOS, and it's going to show us the geometry type application screen. And since we are working with a wire antenna, we'll select the wire antenna application type. And let's first select the wire. So the solid free in this case, so the helix and the feed line. And now I'll be showing you a feature that we are reintroducing into CENOS in the coming week or so, which is the phase definition of the coaxial port. So currently you are able to only select a discrete port, meaning you only select 2 points to serve as the port. But now I'll be adding a coaxial port. So to do this, I'll add the role using the plus coaxial port, and then select the face of the dielectric in our model to serve as the coaxial port. And as you can see, that has been just defined. So I'll just delete the definition for the discrete port. And now we just have to assign all the other solids some role. So let's select dielectric to serve as our dielectric for the coax. Assign dielectric. And let's add another role for the ground plane. So let's choose ground, select that in the model, assign ground, and that's it. So we have just set up our geometry. And now we can just go on to the physical settings part. So here we are greeted by the simulation control, where we select the frequency in which we want to simulate. So I'll do a small sweep. So let's start off with 2250 megahertz, and the end frequency will be 2350, with a frequency step of 50. And as you can see, we have all of our parameters here as well. So that's the bonus of us actually setting up that in Recad. And let's define the material for the coax. So let's go into dielectrics, and let's find in the materials library the PTFE. And press apply. And basically that's it, since ground and wire are automatically assigned as perfect electric conductors. And the coax port is also set up for 50 ohms. So in order to save our time, I have already opened up the results for this case. And here they are. So on the left-hand side, we can see the radiation pattern for the helical antenna in axial mode. This might look a bit weird to you, since the far field here is actually in logarithmic scale. So if I change that up in ParaView to show the far field instead of directivity, you can see a much more typical view of how a helical antenna might radiate in axial mode. So we have our minor lobes and we have our main lobe going directly above the helix. And next up, we can see the Cartesian and polar plots and the frequency charts in the last slide. So basically, that is it for this presentation. This was a rather quick one, despite it being called a complex geometry creation. But as you can see, it wasn't really that hard to create the case in Recad. So yeah, in that case, we can move on to the questions. So feel free to ask. Yeah, feel free to ask any questions that you had about this presentation. So if there aren't any questions, I guess that is it for today. Just a reminder that this presentation was recorded, and you'll be able to view this and maybe even create a log at your leisure. And yeah, we'll be sharing the recording once it is done. So yeah, if that is all, thank you for joining us today and for our quick webinar series, and hope to see you next time when we will be covering meshing inside CENOS. Thank you and goodbye.